Okay, so in this particular case, we've got another combined circuit. It's got quite a few circuit elements. It's got a parallel part up here, the 24 ohm resistor and a 12 ohm resistor. I've got voltmeter 1 measuring around that. It's got an individual 6 ohm resistor all by itself, and then it's got a 3-branch parallel circuit, and within that parallel component, it's got one of the branches which has 2 resistors in series with each other, and then the other 2 branches have 1 branch or 1 resistor each. So there's a lot going on here. As always, the first thing we would want to do is solve for the total resistance. However, to do that, we've got to simplify this circuit. So what I like to do is I like to have a couple cases where I would draw simplified diagrams. So the first thing I'm going to do is I'm going to simplify this part into a single resistor. And then I'm going to simplify these 2 resistors into a single resistor as well. So how do we go about doing that? Well, if I take a look down here, simplified drawing number 1, these 2 resistors are in parallel, so I use the parallel rule of 1 over resistor 1 plus 1 over resistor 2 equals 1 over the EQ, or equivalent resistance. And so 1/12 plus 1/24 would equal 1 over the equivalent, which is 8 ohms. So I can think of these 2 as an equivalent 8 ohm resistor down here. The next thing I can do is these 2 resistors are in series with each other. Well, that's easy to figure out that equivalent resistance, 20 plus 4, since they're in series, and I've given me a 24 ohm resistor. So this is my simplified drawing 1. Over here, what I'm doing is I'm simplifying these 3 resistors into a single equivalent resistance. So once again, these are in parallel. So what I'm going to do is I'm going to take a look, and I'm going to add them reciprocally. So 1 over 24 plus 1 over 12 plus 1 over 8. And you say, well, wait, that's not a 24 ohm resistor, that's a 20 and a 4. Well, its equivalent resistance is 24, so I can treat it like that. So when I do that, I get that this equivalent resistance is 4 ohms. Now it's actually quite easy to figure out the total resistance of the circuit, because I've got 3 simplified components which are all single equivalent resistors, an 8 ohm, a 6 ohm, and a 4 ohm. So overall, that gives me 18 ohms of total resistance. So 8 plus 6 plus 4, 18 ohms. Now to get the total current, and I didn't put an ammeter setting in here for this, but I want to get that first. Using Ohm's law, total voltage over total resistance, 18 volts, 18 ohms, look at that, 1 amp, which is nice. So the next thing I want to do is I need to figure out how to attack certain parts of this circuit. So I've got V1 here, V2 here, V3, and V4 here. So I'm going to look at V1 first. I'm going to use this diagram to help me think about that. So actually either one of these would be okay. So if I think about what a voltmeter would be around this, I know I've got 1 amp total passing through both these components, because the total current in the circuit's 1 amp. So this equivalent 8 ohm resistance would have 1 amp passing through it. So I could say that in this case, this would be my I times Req equivalent. So 1 amp, 8 ohms, 8 volts. Don't know why I put a point over there. Okay, so that's the easiest way to think about that. Now, in terms of solving other things, everything's down here, which is a bit annoying. So I could do the same thing to solve for this voltage across this particular resistor. I could say that's V2. So that would be the equivalent voltage across any of these 3 branches and this component. So I'm going to look at this. I'm going to treat it as an equivalent 4 ohm resistor. And we're going to look at that and say that's 1 amp times 4 ohms. And that's going to be 4 volts. And here I didn't put the point at 0, don't know why. Okay, so that now that should make sense that I've got 8 volts up here, 4 volts up here, and you're saying, well, wait, that doesn't add up to 18 volts, that adds up to 12 volts. Well, remember, I had this resistor over here I didn't ask anything about, but that's going to use the other voltage in the circuit. In fact, it'll use 6 volts up since there's 1 amp passing through it. So 8 plus 6 plus 4 would give me 14 volts used up in any path of the circuit, which makes sense. So the next thing I'm going to want to do is I'm going to attack these currents. The way to think about that is I'm going to use this diagram of the circuit. So I know that the voltage across any of these branches is 4 volts. I just figured that out. And so I'm going to say in this case now, 4 volts divided by 8 ohms would equal A3, because that branch has 8 ohms. So that's 0.5 amps. For A2, 4 volts divided by 12 ohms is 0.33 amps. What about A1 though? We've got two things going on here. Well, A1 has an equivalent resistance of 24 ohms. So I could simply say 4 volts divided by 24 ohms gives me 1/6 of an amp, or 0.167 amps. The other thing I could think about is I know that the total current coming into this junction was 1 amp. That means the total current leaving this junction has to be 1 amp to the law of conservation of matter. So it splits up, and some goes down here, and some goes here, and some goes here. But the total current through these 3 branches has to equal 1 amp. So I could say for this, A1 is equal to A total minus A2 minus A3. So I could say the current through A1 is 1 amp minus 0.33 minus 0.50, and that would equal 0.17 amps. That would be the same thing I would get as if I take 4 divided by 24, which is 1/6 of an amp. So kind of neat that way. Once I know the current through this branch, then I can figure out the voltage across each of these resistors. I can't figure out this voltage unless I know the current going through each resistor. And now we've said that that's 0.17 amp, or 1/6 of an amp. So now for V3, I could say 0.17. It's really 0.167 times 20. And I could say 0.17, again, really 1.167 times 4. These two within rounding should equal the total voltage across this branch, which if you recall, we said was 4 volts. So this equals 3.33. This better equal 0.67. And it does. So again, this equals 4 volts total across that. Hopefully that helps as a way of figuring out how to do a pretty big combined circuit. I can't really foresee us doing things more complicated than that.